So yesterday I uploaded the lecture, the recording, and also the notes from the two lectures. I also uploaded, did you guys see, I uploaded two reports from previous projects last year, so you can see how the result look like, but this doesn't mean that the result is accurate. One of them has like a problem with the shear lag, but I was just like showing you how they were showing the shear lag from each model, how they are showing the inter-story drift and all the information. So that's like kind of can guide you on how to write the final report. And what I'm expecting in the presentation, you present same results but with less wording. Like you just like show more images and just like maybe 3-4 lines describing what is the result is, why the shear lag looked like this, why the shear lag got reduced when we use this system, why the inter-story drift is performing that way, okay? All right, sounds like, and also uploaded homework 6. That's on virtual work. It's gonna be due next week. So maybe you can start now. And also sounds like we only have next lecture. It's gonna be the last lecture. So we are gonna wrap the stiffness method. And we have only one quiz and one homework. So we're gonna have homework 7, and next week we're gonna have quiz number 3 on the, we'll see either the stiffness method or the method of consistent redundance. So next week we're gonna have a bunch of stuff. We're gonna have a quiz, we're gonna have another homework, and the week after it's gonna be actually next week is Thanksgiving, right? The week after, which is gonna be the first week in December. So that's where we're gonna have, as I said, on Tuesday, we're gonna have the midterm 2, or you can call it the final exam. And the Thursday, we're gonna have the project presentation. So I'm expecting we have 3 groups, we're gonna have 3 presentations, and that's gonna be the end of the semester, okay? So that's actually the plan for the next 3 weeks. Is that clear? Does anybody have any concerns, questions? All right, so let's start. Okay, last time I started talking about the stiffness method. I know we're gonna have lots of math, lots of mechanics when we talk about the stiffness method, but it's very, very important to understand the stiffness method, because that's the method that is used by the computer software. So last time we started talking about, like, if you guys remember, if I have a column like this and this column is fixed from here, and there's a load here, and this load is P, and if we want to find the stiffness K, what we should do? Do you guys remember? If you want to find the stiffness of this column, like, okay, you take a sample and take it to the lab, and the lab is asking you try to find the stiffness of this column, the axial stiffness. By the way, when we say stiffness, there's different types of stiffness. Any element, okay, let's say I have this element. When I ask you, try to find the stiffness of this element, that's unclear question, because this element has different types of stiffnesses. You guys tell me what type of stiffness that this element can have. Can have axial stiffness. Like what does it mean? That means the stiffness or the resistance or the rigidity of this element to axial force. That's a stiffness. And also bending stiffness, also shear stiffness, and torsional stiffness. They are completely different elements. So when I say find the stiffness, okay, what type of stiffness, right? Okay, so here, to be clear, I want to find the axial stiffness of this column. I take it to the lab and I try to compress it until it makes unit deformation, right? Once I get to unit deformation, delta equal to 1 centimeter or 1 millimeter, whatever the unit that I'm looking for. So the stiffness K is gonna be B over delta, and since delta is equal to 1, so delta is equal, K is equal to B, right? The force is the stiffness, because stiffness is the force per unit deformation. So if you apply the unit deformation, so stiffness is equal to B. And last time we find out that this stiffness K is equal to EA over L, and that makes sense, because when it comes to axial stiffness, the cross-sectional area is the most important parameter. and definitely the E and L, but I'm talking about something like A and I and all of these things. When we talk about bending, what is the most important component that plays a role in controlling the bending stiffness of a component?
Inertia.
The inertia, right? And what inertia? The inertia about this axis. The axis this way. But if I'm bending this way, what axis is the axis that way? Okay, so it depends on the axis. If we are talking about the torsion, there's something called I total, which is the IX plus IY, both I's, okay? So that's how we control the whole thing. But let's say if I have a member, like a general member, like I said, we talked about bar elements last time, and we had something, and we tried to represent bar as a springs, like spring, like this. So to come up with a general rule of the stiffness that software can understand, we have to understand the degrees of freedom of the member, because this is where deformations can happen, right? Like let's say I have a column like this, and I'm fixing this column here, and I left it free here. So since this is fixed, there's no way that deltas can happen here. So delta is gonna happen here. But the thing is, to come up with a general rule, is that like if I have a member, I'm gonna have a member like this. And I'm gonna assume like it has like, usually if this member is not fixed like this, and it's a free, it's unstable, right? It's gonna be unstable. But the thing is, we find the stiffness for a free member. And then when we try to have this inside the structure, we fix both sides. We fix both sides, and then we deal with them as a fixed. So the thing is, like here, if I come with the stiffness matrix here, like let's say I'm gonna have a stiffness matrix for this member K, and I showed you last time the K of this thing, do you guys remember? It was K, negative K, negative K, K. This is the stiffness matrix of this spring, assuming it's a free from here and free from here. But once we have this inside the structure, we say this one has a degree of freedom U1, and this one has a degree of freedom U2. Like this is U1 and this is U2. But if this is fixed from here, there's no degrees of freedom here, and we make all this line is equal to 0. And if there's no degrees of freedom here and it's 0, so we cross all this line. So there's no way that it's gonna move. Okay? It needs to move so that it can show stiff. I'm gonna show you in detail how we are gonna use that, but I'm telling you why we make a matrix for a free member, like a member like this, how we can drive a stiffness matrix. I'm gonna do the same thing like I did last time. If we have a spring, actually put all the steps here, like, okay, how to build the element stiffness matrix, element, not the structure. So the thing is, determine the element degrees of freedom based on the element type. So this is a spring, so usually the spring has a degree of freedom, 1 here and 1 here. This is U1 and this is U2. Number 2, restrain all the degrees of freedom. So I draw the spring again, and I restrain all the degrees of freedom from the movement, okay? Number 3, assign a unit deformation at each degree of freedom, 1 at a time. That's actually similar to what we have done before. Do you remember when we assigned a unit load at each degree of freedom, 1 at a time? Same thing with the stiffness matrix, but rather than assigning a load, we assign a unit deformation. So I have U1, I have my spring like this. I'm gonna draw it again. All right, I have 2 degrees of freedom. So what I'm gonna do, I'm gonna assign a degree of freedom U1 here, 1 at a time. That means like I'm gonna hold this support and push the support. Okay, I'm gonna push this support. But this one is fixed, is not free. And the second time, I'm gonna leave that alone, and I'm gonna come here, I'm gonna put U2 equal to 1. I put unit deformation, all right? Okay, so that's assign unit deformation at each degree of freedom, 1 at a time, and then calculate the fixed end forces. How can I calculate the fixed end forces? This one has a stiffness K. Okay, all of them are K. So for this support to move a unit deformation, you need a force here. This force equal to B equal K multiplied by delta. K and delta equal to 1. So this is gonna be K. And here, what is gonna happen? This support is gonna resist with a counter force, which is gonna be K, right? How about this one? This one, to push this support that way, you need a force equal to K, right? And this one is gonna have K on the opposite side. All right, I calculated the fixed end forces. Number 4, construct the n by n stiffness matrix of the element, where n is the number of degrees of freedom. So, the element stiffness matrix, we call it K. It depends on the degrees of freedom. It's n by n, so that has 2 degrees of freedom. So I'm expecting to have a stiffness matrix that is 2 by 2. What is inside 2 by 2? It's always K11. Once you go down in columns, you put K2. That's row number 2. Then you are gonna have K21. Here, K1, row number 1, column number 2. And here, row number 2, column number 2, K22. We need to find these. By the way, this column is for U1, and this column is for U2. What does it mean? This K11 so K11, what does it mean? It means that the stiffness at point 1 due to unit displacement at 1. That's K11. This is K21. What does it mean? That is the stiffness at point 2 due to unit deformation at 1. Here, this is K12. 1 means point 1, 2 due to unit deformation at point 2. This is K22 means at point 2 due to unit deformation at 2, and that's actually what we should put here. So K of this member is K and K21. By the way, this is K, but it's in the opposite direction, so we have to put it negative K because that's the positive direction of U2. We put it that way. So we can actually make that as a negative. This is positive, and this is gonna be negative because it's in the opposite direction of U1. So we're gonna have here negative K, K. All right. So that's the stiffness matrix of this member. So let's say if this is 2K or 3K, what is gonna change in this matrix? It's gonna be 3K, negative 3K, negative 3K, 3K. Okay. So that's how we drive the stiffness matrix. But talking about this topic, what if this is not a spring? I mean, like, spring is a bar. I mean, it's like the same like a truss member. Like, let's say that we have a truss here. We have a truss like this, and we wanna find out the stiffness matrix of a truss member. The truss member like, let's take a truss member outside. Like, if I have a truss member like this, what is the degrees of freedom for a truss member? This point can move X and can move Y, right? Let's put U1, U2, and this is U3, U4. That's the degrees of freedom of the truss. If it's a frame, what is gonna be different? You're gonna have a rotation here and a rotation here, which means that this point has a moment and this point has a moment. But the truss doesn't have a moment. The truss, every point here is intermediate hinge. Every point can rotate. It doesn't restrain rotation. All right, so if I wanna find the stiffness matrix of a truss member, I have 4 degrees of freedom. What do you expect K to be? K is gonna be a matrix 4 by 4. It's gonna be something like this. If I wanna find the each element, this is stiffness matrix, I'm gonna do the same. Like, I'm gonna have this bar 4 times. 1, 2, 3, and 4. And I'm gonna apply unit deformation at U1 equal to 1. U2 equal to 1, then U3 equal to 1, and then U4 equal to 1. And then I will try to find the fixed end forces. What does it mean? So I'm gonna fix this. All of them are fixed. Okay. All right, you guys tell me, we know that the stiffness of a truss member is EA over L, right? That's the stiffness. So if you push this that way, you need a force equal to B, which is EA over L, to push this unit displacement, right? And we proved that before. And the same thing here, you need EA over L to push that way. So how about the force here? EA over L that way. How about here? It's gonna push back EA over L. But let me tell you, if you are pushing that normal force that way, EA over L, can you tell me what reaction do I have here? Zero. Why? Because that's the interesting thing about trusses, like, or about normal forces. The normal force on a truss member doesn't impact the moment, doesn't impact the shear on the truss member. It's only axial. We call it, it's an uncoupled force. Doesn't trigger any other forces. But let me tell you something. If you put a shear on a member, like a frame member, the shear triggers moment. Okay? So shear and moments are, we call them are coupled forces. One triggers another. So if you put a moment, the moment is gonna develop shear in the member. But for trusses, once you put axial force, we're never gonna make any shear forces. So this is 0 and 0. Okay, interesting thing also about the truss. If we have a truss like this and it's hinged, if you put a unit deformation that way, it's not gonna trigger any forces that way because the truss only can take axial forces. So if you put a deformation that way, the truss is gonna move. It's not gonna develop any internal forces. This hinge is gonna rotate that way. When it develops forces, when there is a tension or compression. That's the only way to develop forces on trusses. So if you put a unit deformation here, it's gonna be, everything's gonna be 0. Because if this developed the forces, that's not a truss member, that's a frame member. If you put a shear on a truss member, and this shear is restrained, that means that this truss is taking or absorbing bending moment. So it's not a truss member, it's a frame member. But here, it's all equal to 0. And the same thing here, because it's on the other side. So everything is equal to 0 here. How about this one? This one, we put EA over L, and this one is 0, and this one is 0 because there is no shear. So we find all the fixed end forces. So column number 1 is due to U1 equal to 1, and column number 2 is due to U2, U3, and U4. And actually, you can write this as a rows. Like you can put U1 here, U2, U3, and U4. Why? Because one of the important characteristics of the stiffness matrix that is symmetric. Like this is the diagonal, here's negative K, here's gonna be negative K. So if you put this as a row, it's the same as a column. It's gonna be the same. All right, so let's put the elements that we are gonna put here. U1, I'm gonna put K11, K21, K31, K41. K11 is that one, like EA over L. How about K21? K21, 0, because it's this one. Like this is 2, okay, 0. How about K31? Negative EA over L. How about K41? 0. How about U2? All are zeros. It didn't develop any forces. How about number 3? What should I put here? Negative EA over L, because it's this way. So it's going to be negative EA over L. How about here? 0. This is going to be positive EA over L, 0, and all this is zeros. Also, one other thing, all the diagonal members should be positive. It can't be negative. Because that means is, when you put a unit deformation on the member, the force that developed this unit deformation should be in the same direction of the degree of freedom. So it should be positive. Like, it's never gonna happen that the deformation goes that way and the force in the opposite direction. So it's always the force in the same direction of the degree of freedom, which means it's positive. This in the direction of this, and this is in the direction of this. So It's always positive. And that actually makes sense. Like if we eliminate all the zeros and we only consider that this truss member has U1 and U3, so you are gonna end up with like a matrix like this one, K, negative K, and the K equal to EA over L. So it's kinda, this is the same like this, but the spring, we only showed the axial degrees of freedom. We didn't show the out of the vertical degrees of freedom, like U2 and U4. However, in the trusses, we need to deal with it that way because we say as a truss, it can have degree of freedom here, U1 and U2. Maybe U2 is not impacting this member, but impacting this member because it's axial for this member. That's why we need to put this in that way. All right, so let's talk about, so we talked about springs, we talked about trusses. Let's talk about the monastery, the frames. How many degrees of freedom that the frame has? Like I'm gonna put the frame like this. This point and this point. And I'm gonna have U1, U2, U3, U4, U5, and U6. I have 6 degrees of freedom. So how many times should I draw this bar? 6 times. However, if I draw just this 3, I will be able to infer the other 3. It's gonna be very easy to do that because the same way here, can you see? EA over L, all this is 0, and this one is EA over L equal to 0, and this one is the same to this one. Okay, so it's gonna be easy to do it. So okay, so for me, what I wanna find out, I'm gonna draw 3 bars here. I'm gonna handle only this left side. And if I wanna find the first column in the stiffness matrix, actually the stiffness matrix is gonna be 6 by 6. And it's gonna be something big like this. That's the stiffness matrix. We need to find each element in this stiffness matrix. So the first one is gonna be that U1 is equal to 1. Actually, I'm gonna fix all the sides here. All right. First, I'm gonna put U1 equal to 1 and U2 equal to 1. And the third one is rotation. Rotation is I'm gonna rotate that way in the same direction of U3, and I'm gonna put theta equal to 1. Something like this. That's the degrees of freedom that I have. The first 2 is translation. The third one is rotation because it's a moment. Okay? So I put theta equal to 1. All right, so right now my job is to find out what is the forces that is gonna be induced in this once I apply U1 equal to 1. That's actually very easy because this one is the same like this one. Why? Because I just told you that the normal force is uncoupled force, doesn't trigger shear and doesn't trigger moment. So I know for sure that here I'm gonna have EA over L, and here in the opposite I'm gonna have EA over L, and everything's gonna be 0, and even the moment is gonna be 0. There is no moment. It's not gonna trigger any moments, and that's a very easy. So right now, you guys tell me, what should I write here? EA over L, and it's positive or negative? Positive. Here.
0.
And here.
0.
Here.
Minus EA over L.
And here. 0, 0. I got the first column, which is due to U1 equal to 1. How about U2 equal to 1? That's a very difficult one. Why? Because that's an indeterminate structure, fixed. And what is the number of redundants that we have? 3, right? If I want to solve this, at least I have to free this fixed, and then I'm gonna end up with 3 unknowns. What are these unknowns? The vertical, the horizontal, and the shear. But The thing is, the horizontal load, I know that this force is a shear force, is never gonna trigger any axial force. So I know for sure that the X force here is zero, okay? So I can assume it has two unknowns. And to solve this problem for the two unknowns, I need, do you guys remember, I have to pick a main system, and this system should be determinate and stable. So I'm gonna pick this, fix it. And this fix it, and then I put the original load. The original load here is zero, so this is gonna be zero. And then, you guys remember, I put a unit load at each removed redundant. So I have a removed redundant, that one. And let me use that one. I'm gonna put this here, and the second one, and let me put another one here. So that's the main system, MO, and that's M1. And the second one is a moment, right? And I'm gonna put 1. So this is 1 ton, and this is 1 ton meter, and this is M2. Then I will draw the bending moment for each one of these. Here's the bending moment is 0 for the main system. M1 is gonna be positive 1. So actually you can draw the positive top or bottom. So I'm gonna make it like this. That's a positive, and that's equal to L, ton meter. This one is a negative bending moment, so you can have this as 1, and this is as 1, and this is a negative bending moment. All right, and then you start. Here I put the solution of this stiffness matrix by detail here. I solve it like step by step. I'm not gonna solve it to the end. I'm gonna put the final answer. Like if I wanna solve this, I have to solve this like delta 1O, delta 2O, plus delta 11, delta 21, 12, 22, F1, F2. By the way, some of these delta are thetas and some are deltas, because this one is gonna trigger delta, this one is gonna trigger theta, so but I put all of them are as delta, that's fine. And here I'm gonna put delta 1 and delta 2. All right, delta 1O and delta 2O, that means that you have to integrate MO with 1 and MO with 2. What does that mean? That all these are zeros, because there is no original system that has load. MO is 0. So that's gonna leave me with these 4 components to find. So I wanna find delta 1, and that's easy. I'm gonna integrate this with itself. Integration of M1 dL over EI. And delta 2, I'm gonna integrate M2 dL over EI. And delta 1 equal to delta 2 I'm gonna integrate M2 dL over EI. Okay, I can do all that. That's a very, very simple thing. I go to the table, I integrate this triangle with itself, and I integrate this with itself, so I can find these components. All right, so you'll find here that I did all that, I did all the integration, but the interesting thing is, what is the value of delta 1? Is it 0? Delta 1 means that the delta, the initial deformation at U1, at the verse 1, like this one, the deformation that we put here. So that's actually, this is in the direction of this, redundant number 1, and this is redundant number 2. So if one has initial deformation of 1, but delta 2 is 0 because there is no initial rotation, right? If I have 2, like if I told you, I want you to find the reactions here, if there's U2 equal to 1 and theta equal to 1, both of them together, so this one is gonna be equal to 1. But they are not both together. We are doing one at a time. So this one is 1, but this one is 0, okay? So once you solve this, you will find out that, like you will find that F1 is equal to 12 EI over L cubed. And once you solve this, you will find that F2, the moment, is equal to 6 EI over L squared. Let's see if I can remember. Yeah, 12 and 6. So that means that the reactions here, if you have a beam that is fixed from both ends, and you take one end and you shift it by unit displacement, you will find out that this shear, the shear needed to make this displacement is 12 EI over L cubed, and the moment here induced, and by the way, the moment, the tail of the moment is always close to the U2 equal to 1, whereas the displacement is. Like if the displacement is down, the tail of the moment is gonna be the other side. This is equal 6 EI over L squared. And if you, once you find these two, it's very easy to find the other two. You'll find that this goes down, and it's 12 EI over L cubed. And the moment here is gonna be 6 EI over L squared. Once I find this two, it's very easy to find the other two by taking some Fy and taking the moment here. You are gonna find what is the value of the moment here. All right, so I find the reaction that is gonna be induced in this member due to unit deformation, U2 equal to 1. Can you guys tell me what should I write here? I'm gonna put here, that's U2 column. What should I put here?
0.
0, because there is no axial forces. I told you that the shear and the moment doesn't trigger any axial forces. Okay? Here there's no axial forces. It's only vertical shear. How about here? It's 12 EI over L cubed, because that's number 2. We're gonna match number 2, so we're gonna have 12 EI over L cubed. The next 6 EI over L squared, then 0. Then here I'm gonna come here, negative 12 EI over L cubed, and then I'm gonna have 6 EI over L squared. So I'm done with number 2. By the way, in the final exam, I'm gonna ask you how to drive this and do it step by step. You show me how to calculate delta 1, delta 2, 2, delta 1, 2. It might be for this, or might be for that other one, like U3. One of these columns you have to drive it in the final exam. You should know how to do it. How? Like, let's say ask you to do the same thing, but for right now I'm trying to find U3. If I want to find U3, I have to put a unit deformation at 3. So the U3 equal to 1, which is theta equal to 1. Do the same thing in system, and then M1, M2, then put unit deformation. You are gonna end up with having same thing like this one. Like this is gonna be the same like this, and same equations here. Delta 1, 1, delta 2, 2, delta 1, 2 is gonna be the same. Why? Because I have the same thing. I'm gonna put unit load at each remove the redundant, 1 ton here, 1 ton here. I'm gonna have the same bending moment. What is gonna be different? Delta. Rather than having delta 1 equal to 1, I'm gonna have delta 2 equal to 1. Because this is gonna be 0, because I don't have any shear deformation. I only have deformation in the direction of F2. Right? So, and then you will find out that the forces, once you solve the equation, once you do this, you will find that you have a shear here of 6 EI over L squared, and here you will find that 6 EI over L squared, and the moment here is gonna be 4 EI over L, and here is gonna be 2 EI over L. So I'm sure if I still, because I remember when I was in undergrad, I memorized everything about it. Let's see if I memorize it right. Okay, I have this 4, 2, yeah, that's right. Okay, so this one you will find exactly how did I do it here. Like, try to go through it, solve this thing the same like you did this one. You are gonna end up with having same this over there. It's just that delta 1 is 0 and delta 2 is 1, and you will find the new F1 and F2, and you put them there. So here you will find out that this is 0, and then you have 6 EI over L squared, and here you're gonna have 4 EI over L, 0, negative 6 EI over L squared, and then 2 EI over L. Right? I find the 3 degrees of freedom. So you are expecting either this, or even I might ask you on the other side. It's gonna be the same thing, okay? All right, so I'm done by U1 and 2 and U3. So let's see how can we find the other thing. So for this one, the diagonal here is gonna be the same as the diagonal that we have here. So what I'm gonna put, like look at this diagonal, I'm gonna have negative EA over L, and then negative 12 EI over L cubed, and then I'm gonna have 2 EI over L. And this is zeros, 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 like same like this one. So the thing is, the problem is that with these two, so this one is gonna be positive 6, like I'm gonna change the sign of this one, 6 EI over L squared, and this one is gonna be negative 6 EI over L squared. I'm gonna do the same thing with this one. I'm gonna put it here. I'm gonna put the diagonal the same, EA over L, 12 EI over L cubed, and then I have 4 EI over L, 0, 0, 0, 0, and I'm gonna have, off diagonal is gonna be change the sign, so you're gonna have negative 6 EI over L squared, and you're gonna have here negative 6 EI over L squared. And that makes sense. Why? Okay, I'm gonna tell you how do I would, if I wanna double check. Like let's say I have my beam like this, and I said that I'm gonna put a unit deformation in the direction of U5. U5 equal to 1. So I wanna find, this is U4, U5, U6. To do this, I should have in this direction, you see I have 12 EI over L cubed, so I'm gonna put 12 EI over L cubed. And this to be stable, I need to have negative 12 EI over L cubed, so that can be stable. As I told you, like there's a moment should be here, and the tail of the moment is in the same side where you have displacement. And this one is gonna be the same like this one, 6 EI over L squared. And this one, you're gonna end up with having a moment in this direction, 6 EI over L squared. Why? Because 6 EI over L squared plus 6 EI over L squared, both of them are in the same direction, is gonna give you 12 EI over L squared. And when you find the moment that comes from these two moments that makes a couple, so you multiply 12 EI over L cubed by L, is gonna give you 12 EI over L squared. So it's gonna be the same thing. If you wanna find it by statics, take the moment here. We'll find that this one is 6 here. So let's put this at 5. You are gonna have 0, and here you are gonna have negative. This one is negative because it's going down. Negative 12 EI over L cubed, and this one is negative 6 EI over L squared, then 0. Then this one is positive 12 EI over L cubed, and this one is negative. Okay? Same thing if you did rotation. Like if you did rotation, make sure that you make the rotation that way because that's the positive way. U6. All right, so that's the stiffness matrix. Is it difficult? It is. But that's how advanced structure analysis is. You need to know where this came from. Okay? Where every one of these columns came from. Actually, gets very complicated. Right now, I give you this member horizontal. What if I give you this member not horizontal, something like this? And there's an angle theta. You need to get into transformation matrix and you need to multiply by transformation matrix to get what we call the global stiffness matrix. Global stiffness matrix is a matrix for a member that has an angle theta with the horizontal. So you will end up with a matrix like this, but has lots of sines and cosines, okay? Let's not talk about it right now, and let's focus on what we did in the last, 45 minutes. We developed the stiffness matrix of a spring, we developed the stiffness matrix of a truss, we developed the stiffness matrix of a frame member, okay? So you need to know where all these came from. And we did that right now. I told you where this came from, where this came from. And in the midterm, I'm gonna ask you to drive one of these columns. You need to know where each column is coming from. Like for example, this one, actually I put also in the notes, how did I got EA over L? There's many ways to get it. And I showed you one before, and actually in the notes, I put this one. In the notes, I solved this one using this concept. Like the concept of consistent redundant. I remove this and I put a unit load and then get delta 1 and I put how did I got it. So go through the notes and see how I derived each one of these, okay? Because it's gonna have like at least 25 points in the midterm exam. You need to know where all these came from, okay? All right, so does anybody have any questions so far? All right, so right now we saw how can we develop element stiffness matrix. That's called element, that is called an element, that is called an element. Let's see how we can use this in driving the structure stiffness matrix, like solving real problems, okay? So I'm gonna work on the other board. I'm gonna start with a spring system. So let's say I have a spring system like this. And it's connected to 3 springs. Spring in the middle, and 2 springs on the other side. And this system only allowed to move in the x direction. Like you have a solid block here, and the stiffness of each one of these springs is K. Okay, and there's a force here. This force is 10 ton, and this force is 10 ton. And I'm asking you, determine the forces in each spring. Well, can you guys tell me, before even I solve this problem with the stiffness method, what is the force in each spring is? Before I do any math.
10, 0.
By the way, you are saying this is 0, but this is a solid block. If it's moved that way, this spring have to move. It's gonna have force. So what is gonna happen? And all of them has the same stiffness, K. And it's either we all move together or nobody's gonna move. So they are all gonna move. If this system is gonna move that way, that means these 2 springs are gonna have tension or compression? Tension. And this one, compression, because it's gonna be compressed. If this is moved that way, these 2 springs is gonna be compressed and this one is gonna be tension. So all of them are gonna have the same force because they all have the same stiffness, but some of them are gonna have tension, some of them are gonna have compression. And since they all have the same stiffness, and so this 20 is gonna be distributed equally on the 3 of them, right? Do you guys remember when we did the summation of springs in parallel? It's the sum of all of their stiffness. So this entire system has a stiffness of 3K, right? They are all in parallel, right? And they are under total force of 20. So if you want to find the delta is going to be equal to B over K, so it's going to be equal to 20 over 3K, right? And from my perspective, this 20 is going to be distributed equally. So this is going to have 20, and let me tell you, where's this system is going to go? That way or that way under these forces? That way. So I understand this is going to have compression negative of 20 over 3. And this is going to be 20 over 3. This one, positive 20 over 3. That's like common sense without doing any math. But let's see how we like use the concept of stiffness to drive these forces. Versus step by step, I put for you here, what is the steps to solve, how to solve using the stiffness method. Number 1, determine the number the members in the joints. So what I'm gonna do, I'm gonna say that this is member number 1, this is member number 2, this is member number 3. Okay, number 2, determine the degrees of freedom. You guys tell me, how many degrees of freedom that I have here? I mean as a structure, not as members. That this structure, how many degrees of freedom? Is it allowed to move up? Is it allowed to rotate? It's only allowed to move that way. That's only one single degree of freedom. Like this system is only allowed to move U1 as a structure, as a system, U1. So I only have single degree of freedom. All right, so number 2 is determine the nodal and fixed end forces. Okay, let's see what is the nodal and fixed end forces. So I put it here not in order. I tried to find the structure, but it doesn't matter. Like it's gonna be the same thing. I'm gonna take each spring alone, okay? That's a spring number 1. That's a spring number 2. That's a spring number 3. That's K, K, and K. Nodal forces, that mean the force at a degree of freedom. I only have a force at degree of freedom here and a force at degree of freedom here. That's the forces at the degrees of freedom. But if I found it for each member, okay, first let me put the fixed end forces. Fixed end forces for member 1, fixed end forces for member 2, fixed end forces for member 3. Fixed end forces, that means, what does it mean? That means like if you have your spring in a fixed position, fixed, is there any force inside that triggers any fixed end forces? No, there is no any forces in between here that can make this spring move. But if this is a beam and has loads inside, this load is gonna trigger fixed end forces. So this is gonna be 0, and by the way, that should be a vector. Why? Because each spring has 2 degrees of freedom. I need to find the fixed end force at degrees of freedom 1 and degrees of freedom 2. So all these are 0. And that's what we call local fixed end forces for each member. Then second, okay, again, this one represents degree of freedom U1 and U2. I'm saying that the fixed end forces at U1 are equal to 0 and U2 are equal to 0. And by the way, this is element degrees of freedom, not structure degree of freedom, like each element alone. All right, so how about nodal forces? Why I'm doing this? Because you guys, if you remember the rule from last time, F total is gonna be the structure stiffness matrix multiplied by the deformation. Like it's K multiplied by delta, but that's for the entire structure. And if it's an element, it's gonna be F total multiplied by the K of the element multiplied by the U at the element. So it's the same thing. That's for element, that's for the structure. But F total is equal to, if you guys remember, it's equal to F nodal minus F fixed end forces. And I told you why did we come up with this thing last time. So we can write that F nodal is equal to, like I can substitute this here, is equal to F fixed end forces plus S multiplied by D. And I'm gonna tell you what I'm gonna do is this right now. Let's first find the fixed end forces. We did. Nodal forces, I can find the nodal forces for number 1, number 2, number 3. Okay, so nodal forces for member number 2, I have a nodal force here is equal to 10. And I have 0 here, and it's positive. It's in the direction that way. And sorry, that's not 1. That's 2. Sorry. Number 1, I don't have any nodal forces, right? 0 and 0. Number 2, I have 10 and 0. Number 3, 10 and 0, right? Okay, that's 4 members, okay, for each member alone. Let's find about the structure. The structure only has 1 degree of freedom. Like when I built this, I assumed that this point is moving and this point is moving. This point is moving and this point is moving. But this is as an element. But when we put this in a structure, actually there's only 1 degree of freedom, and it's at this node here, at this node here, and this node here. So from what I see is, here there's no degrees of freedom, 0 degrees of freedom. There's U1, which is the structure, 0, U1. This one has U1, 0. I have U1 here, this degrees of freedom is gonna move these 3 points, but it's not gonna move this point. And this one is gonna have U1 and 0, same thing. I'm gonna have 0, U1, U1, 0, U1, 0. So if you wanna find the fixed end forces for the entire structure, and actually it's only one element because it's only U1. So it's all equal to 0 and it's only 1. Why be only 1? Because I only have 1 degree of freedom and it's all 0. So what I do is 0 plus 0 plus 0 is gonna give you 0. And if you wanna find the fixed, the nodal forces at U1 here, so I'm gonna pick this 0 plus 10 plus 10 is gonna give you 20. And in summary, actually I could have done without going all this. I know that none of them has fixed end forces, so the fixed end forces in the direction of U1 is 0. And I know the forces, the total forces in the direction of U1 comes from this one and this one, so it's 10 plus 10 is equal to 20. So the total forces that push all these springs coming from nodal forces equal to 20. But I did this system to be systematic, to know how this problem be solved step by step. All right, so I'm done with F nodal and F fixed end forces. Let's find the structure stiffness matrix. How to find the structure stiffness matrix? Okay, I'm gonna build the stiffness matrix of each member. Member number 1, member number 2, and member number 3. So let's put that here. K1 is gonna be equal to K, negative K, negative K, K. And K2, same thing. K, negative K, negative K, K, and K3 is gonna be equal to K, negative K, negative K, K. That's the 3 stiffnesses for the 3 members. Then I'm gonna put the degrees of freedom on each one of these stiffness. I know that this member inside the structure doesn't have any degrees of freedom. So this one doesn't have degree of freedom, but this column has degree of freedom U1. Okay? You can put them here, 0 and U1 as well. How about K2 has degree of freedom here or here? At the left side. So you are gonna have U1 here, but this one has 0. And this one has U1 here, 0, U1, and 0, right? So there is no way that this one is gonna move or this one gonna move. So since there is no way that this one is not gonna move, so you can cross this and you can cross all the zeros and you are gonna end up with one single K. Same thing here. This is 0 and this is 0, so that's the stiffness that is contributing. And this is 0 and this is 0, so that's the stiffness that is gonna contribute. So if you wanna find the structure stiffness matrix, and by the way, the structure stiffness matrix is N by N. What does it mean? N is the total degrees of freedom for the entire structure, and I only have U1. Okay, so this is gonna be 1 by 1. And how can I get it? This plus this plus this. So you cross all the zeros and you are gonna end up with KK and another K, so that means that is 3K. And that's what I did actually a few minutes ago. I told you that all these springs are in a parallel. So if you wanna find the total stiffness, you sum all the K's and you're gonna end up with 3K. All right, so that's the structure stiffness matrix. So I'm done with this. So if I wanna solve this equation, F nodal is equal to positive 20, plus F fixed end forces is equal to 0, plus S is equal to 3K, and I wanna find the displacement D. What is the displacement D? What is the actual displacement at U1 due to 20? So D is gonna be equal to 20 over 3K, right? It's a very long and tedious to get this, right? Even that from verse we can say, I have this system in parallel, 3K, 20 ton is pushing that way. So if I wanna find the delta, delta is equal to 20 over 3K, right? But actually, that's not how the computer solved this problem. The computer solved this problem by doing all this, developing all these matrices, is because that's how he thinks. All right, so I done with D, but I didn't find the forces inside the spring. If you want to find the forces inside the spring, the force, the nodal force in the spring is equal to the fixed end forces on the spring plus the stiffness matrix of the spring multiplied by the U at the spring. So if we want to find the nodal forces in member number 1, it's going to be the fixed end force in member number 1, which is 0, plus the stiffness of member number 1, K, negative K, negative K, K, plus the U on member number 1. The U on member number 1, actually, there is no U here. It's 0. This point never gonna move. Here, the second point is gonna move by D, which is 20 over 3K. So if you wanna find it, you guys know how to multiply matrices? It's gonna be here, 0 plus this row multiplied by this column. K multiplied by 0, 0, negative K, so this is gonna be negative 20 over 3. And this row multiplied by this column, so this is gonna be 20 over 3. So that means that this member is gonna have negative 20 over 3, and this one is gonna be positive 20 over 3, so it's gonna be under tension. And that makes sense. This is gonna be something like this. And then you can do the same thing and find the force number 2. And this is gonna be 0, 0 plus K, negative K, negative K, K. And you guys tell me, what should I put here? 20 over 3K. And here? 0. And then you are gonna find 20 over 3, negative 20 over 3. And this means that here is positive and here is negative. And you are gonna do the same thing for member number 3, and you are gonna end up with the same thing. All right? I know it's difficult, but by the way, that's only 1 degree of freedom. We didn't get to the 6 degrees of freedom, the monastery. It's a hell of a problem if you did. But okay, so right now you understand how we do it. Let's go to a little bit of a step of difficulty. So usually springs that are in barrel, it's much easier than the springs in series, because in series you can sum the springs together. You guys remember? So our next problem is a spring system also. And I'm gonna put the problem here. So I'm gonna have a spring like this and connected with a spring like this and another spring. And I'm telling you here that the K of the springs, that's actually K. That is 3K. And that one is 2K. And I have $100 here, and I have 20 ton here forces. And by the way, I have displacement 2 centimeter here and 1 centimeter here. Okay? And I'm telling you that the K, the stiffness K is equal to 1,000 ton per meter. And I'm asking you to find the force in each spring. We are gonna do the same thing. As a structure, how many degrees of freedom does this spring system have?
2.
Where are these 2? Here, this one can move U1 and this one can move U2, right? That's 2 degrees of freedom. There is no degree of freedom here and there is no degree of freedom here. All right, so we have 2 degrees of freedom. And then we're gonna do it step by step. I wanna find the fixed end forces and I wanna find the nodal forces. Why? Because at the end, I wanna substitute with them in the structure stiffness equation. Okay, to do this, I have to take each spring alone, fix all the degrees of freedom. So I have spring number 1, I'm gonna fix it. And I have a spring number 2, I'm gonna fix it. and I have spring number 3, I'm gonna fix it. But then you have to number them. 1, 2, and 3, so that we know what we are doing. And by the way, when we take them out, we need to put all the forces that is gonna make fixed end forces. Like what? This 2 centimeter is gonna make fixed end forces. And this 1 centimeter is gonna make fixed end forces. Nodal forces is the force at this node. So I have these forces is making nodal forces. All right. So let's find out about the fixed end forces. Let's say this has K, this has 3K, this has 2K. Does this one has fixed end forces?
No.
No, because all the forces added is nodal forces, right? Okay, so there is no fixed end forces are 0. How about this one? To develop a 2 centimeter in an element that has K stiffness, you need a force here equal to K multiplied by, and K here is 1,000. So if you multiply 1,000 by 2 centimeter, which is by the way, this is ton per meter. So this is need to be 0.02. 0.02 multiplied by 1,000. So you're gonna have here 20 ton and 20 ton. That's the reaction that comes with 2 centimeter. Why? Because if you compress this 2 centimeter and the stiffness is K, so B equal to K multiplied by delta. K is 1,000, this is 0.02, so you have 20. How about this one? 2K, 2,000 multiplied by 0.001. 20 and 20 ton. So right now I can put that the fixed end forces for member number 1, and by the way it has 2, so I'm gonna have 20 and negative 20. That's for member number 1. Fixed end forces for member number 2, 0. Fixed end forces for member number 3, negative 20 and 20. All right. How about nodal forces? Member number 1, I'm gonna assume this nodal forces on this member. So I'm gonna say that this member has 0 and 0. You cannot double the forces, the nodal forces in one member. So, and then F nodal for member number 2 is gonna be negative 20 and positive 100. Nodal forces for member number 3 is gonna be 0 and 0. So you'll find that I have done everything here. By the way, if you wanna skip this step and you know from verse that by the way, this is the F fixed end forces at the member. And why I'm doing this? Because I wanna get at the end and find the fixed end forces for the entire structure. And since I have 2 degrees of freedom right now, the fixed end forces for the entire structure is gonna have vector that is 2, one for U1 and one for U2. And to do this, I need to put here that this has 0 and has U1, like 0 and U1. And F2 has U1 and U2, U1 and U2. This one has U2 and 0. Same thing here, 0, U1, U1, U2, U2, and 0. So to get the fixed end forces for the entire structure, I'm gonna sum U1 with U1, because I only have U1 and these two, so it's gonna be negative 20. And here U2 is 0 and negative 20, so I'm gonna have negative 20, and that's it. I'm done with fixed end forces, and that makes sense because I want to find out what is the fixed end forces at U1 if this is moved 2 centimeter. If this is moved 2 centimeter, this one is going to have a negative 1, like going that way because it's going to compress in the opposite direction, negative 20. And if this one is moved 1 centimeter, this one is going to have negative 20 on the other way. Nodal forces for the entire structure, same thing. 0 plus negative 20 and 0 plus 100, so you're going to have negative 20 and 100. And actually we could have done this without going through all that by looking at the nodal forces directly at the degrees of freedom without going through the element. If you want to do this in the exam, you can do it. Like just put Fn by just looking at the forces right at the degrees of freedom. Same way here. I know that I have 10 and 10 in the direction of U1, so I have 20, where did I put it? Here as F nodal. Okay, so I'm done with the first step. The second step is to find the structural stiffness matrix. Okay, to do this, I have to put K1 of element number 1. You guys tell me, what should I put here? K, negative K, and K. K2, 3K, negative 3K, negative 3K, and 3K. K3, 2K, negative 2K, negative 2K, and 2K. All right, then I'm gonna put the degrees of freedom. Where do I have degrees of freedom? I have 0, like this member only have degrees of freedom at number 2, at column number 2. And this degrees of freedom is number 1 for the structure, 0 and U1. How about this one? This one has 2 degrees of freedom, U1 and U2. Why? Because this member is the middle member, has U1 and U2. U1 and U2. K3, U2, 0, U2, and 0. Okay, I'm gonna cross all the zeros. I'm gonna have zeros here, I'm gonna cross all the zeros. So if I wanna build the structure stiffness matrix and we call it S, you sum everyone with its corresponding degrees of freedom. So I have U11, and here's U11. So this is gonna be K plus 3K, okay? And I'm gonna have 3K plus 2K because that's U22 and U22. Look, U2 and U2. So this is gonna be 3K plus 2K. However, these two doesn't have a corresponding from here or here because that's U21 and that's U12. It doesn't have anything here. So I'm gonna leave these as is, negative 3K and negative 3K. And now I built the structure stiffness matrix, which is gonna be equal to 4K, negative 3K, negative 3K, 5K, 2 by 2. Why? Because it has 2 degrees of freedom. Right now, I can find the deformation. What is the deformation? I wanna find what is the actual movement here and what is the actual movement here. So I'm gonna substitute in this equation. F nodal is gonna be equal F fixed end forces plus S multiplied by D. D is the displacement, the actual displacement. So F nodal, we just got it, negative 20, 100. F fixed end forces, negative 20, negative 20. And the structure stiffness matrix, by the way, this is 4,000, negative 3,000, negative 3,000, and 5,000. And the displacement 1 and displacement 2. Okay, actually put them as U1 and U2, so it's the same thing. We can put them as U1 and U2. You can solve this, I believe, on your calculator. It's two equations and 2 unknowns, or you can put this matrix in the calculator and you end up finding U1 and U2. This is gonna be 0.033 and this is gonna be 0.044 meters. Are we done? No, we are not done. We only find the displacement. We need to find the forces. So to find the forces, the force in member number 1 is gonna be the fixed end forces in member number 1 plus the stiffness matrix of member number 1 multiplied by U of 1. So fixed end forces in member number 1 is 20, negative 20. K of member number 1 is 1,000, which is K, negative K. And U, and member number 1. U member number 1 here is what? Is 0, because there is no U that's gonna happen here. Right now we found the value of U1, 0.033. Once you solve this, you will find what is the actual force that you have here, which is gonna be negative 13 and positive 13. Same thing, you are gonna do it for member number 2. Member number 2 have fixed end forces of 0. Do you have any?
I see. I was looking why you become
okay.
positive 20
So,
and negative 20.
Yeah, so basically, yeah, the equation of the element is the same like the equation of the structure. This is like this one, but this is the structural nodal forces, the structure fixed end forces, the structure stiffness matrix, the structure displacement. This one, but this is the element nodal forces, element fixed end forces, element stiffness matrix, and element displacement. The element here is not moving, it's a 0, but here it has U1. Okay, same thing, but this element has actually moving here and moving here. So I'm gonna put the stiffness matrix is gonna be 3000, negative 3000, negative 3000, and 3000. And here I'm gonna have 0.033 and 0.044. And try to find, it's gonna be negative 333 and positive 33. Okay? And I'm gonna find F3 the same way. Fixed end forces, negative 20, 20, plus the stiffness matrix is 2000. And it has U2 here, which is 0.044, and it has 0 at the end. And then you will find out that this is positive 68, negative 68, once you solve this. Okay, let me ask this, is that difficult? It is, right? You think so? This is the most easiest stiffness matrix problem, I'm not kidding. And that's only, that has element 2 by 2, 2 by 2. Can you imagine when this becomes a truss, 4 by 4? Or a frame that has a matrix 6 by 6, and the frame is not even horizontal, it's inclined and has an angle theta. It's gonna be much more difficult. Okay, but the way that you can think about it that it's not a difficult problem is that you think systematic. Look at what I have here, step by step, telling you how to develop the stiffness matrix of an element, step by step. Everything that I did, we already go through it from the basics, like how to define the degrees of freedom, which is number 1, how to assign unit deformations, how to define the external forces, the fixed end forces. You can do each step alone, but you know that each step is taking a long time. You're gonna take your time in the exam, just substitute in the steps. Like think about it, what we did here. Have a spring system, isolated every one, fixed it, and got the fixed end forces. And then got the nodal forces by looking how's the nodal forces look like. So we finish this, we finish this. Then for each spring, we put the stiffness matrix. We know actually, we spend the lecture knows where's this stiffness is coming from. We put this alone, and this alone. Then maybe it's a little bit difficult to make this free, construct this thing. But I told you, put the degrees of freedom at each one, cross the ones that are zeros, and you are gonna end up with the ones that add the degrees of freedom. This is something like, this is the stiffness matrix of member number 1, and this is member number 2, and this is member number 3. So we only want this. This one is zeros, and this one is zeros. So we sum this with this, and this with this. That's the one that has U1, U2, U1, U2. That's how we get the structural stiffness matrix. Once we get the structural stiffness matrix, substitute in the equation of the structure. With the nodal forces vector, the one that you did here, and the fixed end forces vector, and the structural stiffness matrix, and multiply, which can be done in your calculator to get U1 and U2. And then for each member, you are gonna be doing the same. Step 1, step 2, step 3. So from my perspective, I see it's all steps. If you systematic your way in solving the problem by going step by step, it's gonna be easy. It's long. It's a lot of math, okay? But you need to do this because next lecture is gonna be much more difficult because we are gonna deal with stresses that our stiffness matrix is not 2 by 2 anymore. It's gonna be 4 by 4 and 6 by 6. So you need to practice. I'm gonna upload the homework on this part. So you need to practice how to solve these, okay? All right, so see you guys next time, and try to practice more on this, and next week we are gonna have a quiz. So, and I believe it's gonna be something on these things, so try to practice as much as you can.
What will it be, Saturday or Tuesday?
I'm gonna decide the day, maybe not Tuesday. give
It
me-
has to be Tuesday because Thursday's Thanksgiving.
Okay, I mean, like, maybe when, like, I can open it on a different day, like, you guys can choose what time that you wanna do the exam.
Wednesday is it.
Wednesday is good?
Oh, no, we have an exam.
Okay, so let's make it Tuesday, okay?